Can you see? Here we go. So our topic of our meetup is exploring the Lisp from code examples to formal proofs for CPU's blocks. I'm encourage you to open your text editor and start coding a Lisp with me. So today we are going to do some code examples, start to using ACL2 theory improver, and we will do some example proofs in this system, and then I will describe a motivation for hardware verification and how it works. Then we will dive deep into the what's the arithmetic logic unit and how can addition in the CPU can be implemented. So in our first example, I would recommend to you check this function. This is an example of the recursion. So as you can see, we have here if n less than 1, then we should return the integer equals to 1. Else we have to calculate the multiplication of the n and this function from n minus 1 step. So to start coding a Lisp, I would recommend you to open this website, which is called the CodeWars dashboard, and here you can find some interesting code examples or tasks which you can train and implement by your own. You can do it with fundamentals, rank up, and practice. So it's for example useful for training a common Lisp language in the CBCL version of Common Lisp. Another book which I would recommend, it's a Practical Common Lisp. As you can see, there are different topics. How can we implement database, web programming, basic file and input and output, etc. So here, how can we do some basic operations like an addition, subtraction, multiplication, and division. So let's check how it can be implemented in the real coding environment. So we will start our virtual machine. For example, this is a common Lisp command line interface. How can we implement, for example, addition? 5 plus 4. What will be the result? 9. So another operation is 5 equals 20. So as you can see, everything in the Lisp is a list. It's like an S expression, which is divided into parentheses. So let's create a list. So for example, it's this graphical user interface. It's just a standard Emacs text editor, which can be used for various tasks. For example, compile Lisp programs. So, for example, we can start from this basic construction, which is called def-var. Then we have to name a list. The beginning of the list can be implemented from this operator, or we can just type implicitly list. So we have list of numbers from 1, 2, 3, 4, 5, and it will be assigned to the numbers. So let's compile. Compilation. Yep. And here we can check what the numbers is. So as you can see, we have some debugging in the command line Lisp, and it can return some error values and some retry functions, which is can say to us numbers, if for example is not defined. So let's go back to the code. Come here. So how can we solve this task? Any suggestions?
So what do we need to do again?
We need to compile this line and print on the screen the values of the numbers.
So yeah, we can do a loop across all that, across the list.
For example.
And print every value with format.
So how can we implement a loop?
With loop.
Loop. Yep.
For actually, yeah, for I from actually no, for I from numbers. Yeah, actually, I think I forgot the syntax a bit. So yeah.
So we should verify this.
Yeah. In, yes, in, and then, yeah, in numbers.
And the body of the loop, we are going to do some format.
Yeah, you also need to have do after numbers.
Yep. Format. And what should we do? We do some formatting, which is this one.
No, it's actually it's a different format. Tilde A.
Oh, the A. Yep.
Yeah, tilde. And then we can add a new line with tilde %. No. Yeah, as I said, you need also to do after the variable. So after numbers, yeah, to specify the actual expression that you are evaluating in each iteration. No, after the numbers, yeah.
Yep, here.
Yeah.
So how can we do this?
Just try to
Do.
yeah, like this.
Let's check.
Yep.
Yeah. So as you can see, we have printed the output from the numbers to the screen. How can we implement hello world? So let's start from def1 function. Yep. So then name, for example, green. It does nothing in the input, and we will print on the screen just the string hello world. So let's check. Compiling, and then we do green. Yep, it works. So the next step is how can we accessing the first element of the list. So let's check what's the output of the numbers for the first element. At least we have to start a new parenthesis and put into this parenthesis our function from the basic library, which is called first. It's a reserved function for the lists, and here we will put our list numbers. So it equals 1. Another basic functions, it's cons, which is adding the element to the list. It's same as a concatenation from the with the value and the list. So how can we find the length of the list? Let's check this. It's reserved function numbers. Yep. So the length equals 5. That's correct. So let's define the square function, which calculates the square of x in the power of 2, and obviously square of 6 equals to 36. Then we have if statement, if expression in the list, which looks something like this. So this function checks that if x is odd or even. So if we put this into this special function that implements this decision, we will put if it's equals true, it will return even, and if it's not, it will return odd. Another interesting example is our higher order functions. We can specify, for example, lambda expressions. We can specify another functions which we can call as an argument to another function. As you can see, we can implement this kind of function, which is gets the argument as some function arg, and we do some function call here. So here do some function call for apple twice, and it will do execution of this function double 2 times. Let's check this. So as you can see, I have found Lisp notes, which is Lisp cheat sheet, which is quite useful for beginners. You can find the basic constructions, the list of the global variables, global function, how can we manipulate with lists, how can we manipulate with another logic and blocks. And another important construction is the structure, where we can put all of the necessary functions, variables, etc. in the one data type or structure where we will wish to implement. So the main topic of our meetup is this list, 99 Lisp problems. which is quite useful for beginners to understand any functional programming language. It helps to, which is based on a Prolog problem list. This 99 Lisp problems was implemented, for example, for Haskell, for standard meta language, and other languages. So the main interesting feature of this list is which we have to work with different basic data structures, such as lists, graphs, trees, subsets, do some arithmetic, and maybe hash functions where in some cases we can implement, and solve some standard problems from the theory of programming from computer science, such as 8 queens problems, night tour, like solving a Sudoku. For example, in the future I can show you, for example, how can we implement SMT solver, execute inside the Lisp, and solve the Sudoku problem, which is quite standard and common problem. So the first problem which I want to describe is how can we find the last box of a list. So the implementation should be the following. So we have to write the function mylast, which gets the list from as an argument, and return the last element, which for this example is equals to d. Let's begin. I will erase all of this and start writing the function. Last list. So here we can put an if expression, which puts into the parentheses. So if now list, yep, here we should return nil, which equals to empty list. So if we have now plus the rest of the list, here, then we should return a list. Then we do the following. We do some recursion. My last element, and we put here the rest of the list. This one, let me check, just all okay with parentheses. Then it goes here and here, yes. Now we are able to compile this. So let's check my last. Yep, that's correct. We have implemented the first task from this list of problems, 99 list problems. So the another problem is find the last box of a list. So how can we do this? Find the last box of the list, which is, for example, my.last equals this one, and we have to implement this function. So let's continue. Maybe we should do a reverse function at first, because it's easier to understand. So the output of this function will be the same list in the reverse order. Inverts. So, and so here we should create another function which is called auxiliary function. Inverts auxiliary function, and we put here a list. Then in the auxiliary function we do the following. Inverts auxiliary function, have the rest list, if null list rest, and we put into the rest function the step or the recursion of this function. So it inverts auxiliary function here, and rest list, and do some concatenation, which is cons first list. Then we should do the following. Rest. Okay, so I hope everything is alright, and let's compile the whole file. Yes. Yes, the compilation is finished. So we can try this one. Alt W, and the paste it's Control Y. And here we will change this one. Inputs, and so input is undefined. So, any suggestions? What's wrong with this?
Can you open the, I think there is a separate buffer for compilation errors maybe?
Here?
Yeah.
So,
Cloud the buffers.
this one.
Maybe this one. to call that buffer and we can find the one with the
We can do the following. We can do the completion. Compile file.
buffer is interesting.
So compilation equals compile file.
I think you need to compile also. I mean the other option, Control C, Control K.
Control C, Control K. Yeah.
Yeah.
Yeah. So let's check. The compilation thing aborted with undefined function inverts. Inverts.
I think you need to inverts when you have an empty list. I think you need to add a code for it so it can be evaluated. No, I mean, so the second argument for inverts AUX inverts inverts. Yeah. No. I mean, yeah, here.
Yeah.
No, it's in the inverse definition where you call inverts AUX.
Yes.
You need to add the code to the second argument where you have the empty list, so it's trying to evaluate an empty list instead of
Yeah. This one.
If I understood correctly.
Yes, that's right. So let's see.
Yeah, you need to see the task field, so you need to press Y. Okay, it's
So let's check some inverts. Inverts. So what's the logic of this? So we put here a list and we have to do some rest of the list. Maybe
and it looks at so it sees that your second argument is empty and returns the first argument if I understood your function correctly.
yeah.
So because of that it returns your input list because the second argument is empty.
Yeah.
Or so the intention.
So what's the reason why is it not working? Let's X. So this is the reason why we should verify those functions. Because in some cases those functions are not total. They are not defined for every possible argument. So as you can see, if we just mistype something, it should go to the infinite loop. Yeah, so interrupt this process. Abort. Yep. Aborted on nil. So how can we solve the reverse problem? So as the input of the problem we have some list 1, 2, 3, and we should return 3 to 1.
Oh wait, you have that list you have only one value there.
If null list, then the rest of the list should be inverted as a first list. So you can find a cheat sheet in the list functions. So here we have some basic functions which is called nth, which return the third element of the list. The same principle for this type of things. We have the last element, a very useful function for access some things. So let's remove this one and return last. Evaluation aborted on nil.
I think it shows the condition maybe in another buffer.
Yeah, yes, you're right. So we'll just check this one. Yeah, it shouldn't. It should work, but it shouldn't. So what's the issue?
So the issue is that when you inverts, you call inverts AUX, you pass some list and you pass an empty list, but when you pass it an empty list, it just returns the list when you do that. So it doesn't even go to that inner part. It terminates on the first clause of the. So
Here.
no, I mean, yeah, received rest when. So yeah, it just returns rest and stops. It doesn't go through when you call it. I think.
Okay, so maybe something with the parentheses. So
I think.
so if we have the null list, which is empty list,
Yeah.
we will return the rest.
Yeah. So, but your second argument of this function is an empty list when you call it in the other function. So rest is your normal list, or your and or which one you pass through inverts, and the second one is an empty list. So it just returns rest and it doesn't call it recursively.
So let's check the solution. Okay, reverse list. So as you can see, we just can rename this list. Rest. For example, inverts. At first we have the list, and then we have to return the rest. List. Then we should go to here. the rest list. Rest list. Yep. And then in the recursion we will go to the rest list.
Yeah, now it makes more sense.
Yes. Now we can just rename this as a list. Here we put a list, and here the reserved function with rest and rest.
I think kernel is the same as this basically.
Rest. Rest. If now list. Rest.
Okay, now
Yeah, now that works. So, as you can see, we have some solutions from the official website. So the next interesting problem is which is sorting a list of lists according to the length of sublists, which is quite a tough problem because due to amount of code for handle with it. For example, as you can see, sort solution is here. So it's not quite easy to implement right now because there is too much code for this. Yeah, it's quite tedious to write down all of this. Just let's look what's going on here. At first we will return a list ordered according to the size of the subsets, which is this function. Then we return a new list with elements of the form, this one, where n is a frequency on the size of the element list and lm is a sublist. So we are sorting a sublist of the list. The initial problem looks like this. Sorting a list of lists according to length of sublists. We suppose that a list contains elements that are lists themselves. The objective is to sort the elements of this list according to their length. Short list first, longer list later, or vice versa. For example, we can call this function and we have to sort it by the length of the sublist. So as you can see, that's why we returns of a list of ordered according to the subsets, which is this function. For this function we have to implement the frequency function, which has some key insights about this. For example, we receive a list with elements of the form, for example, chief element, which is like key elements, counts of number of the sides of the original lists, and return a list of the ordered by the frequency. So here we have some function sort, originated list, put here some key and length. Origin list, it's our argument. So it's like it's a special function for here to implement some key performance. So sort mark. Another interesting problem is a list of prime numbers. Here we can determine at primes between k and n. So we can determine what's the prime number between those numbers. So we have to find the primes before some value k and primes after this value. So we have to remove all of the values before the k with using this function, remove smaller from the list, and remove up to n, which is both the n from the list. So we have to return a list with primes up to n in an ascending order. Accumulating auxiliary functions, we can calculate for the for all other primes from k to n, which implemented using this function. So this is a condition value k. So we are using some predicate which goes here, which with this construction is called the lambda function, which implements the some argument from the list, which for each element of the list we implement a lambda function with following expression. So it modulus of k by x equals to 0. So it's like a division without it. Another interesting problem is the string representation of binary trees. So binary trees. Symmetric. Here we go. Somebody represents binary trees as strings of the following type. For example, A is a root, B is a child of A, C is a child of A, D has two leaves, D and E. So we can write a function which generates this string representation. If our tree is given as usual, then write a function which does this in verse. Given their string representation, construct a tree in the usual form. So, because it's too, it maybe can be too long, so we can implement this and try to check this out. Compiling. As you can see, we have some condition value for here, and we have symbol name, first tree, second tree, string representation. So let's test this. For example, here. String representation. So, as you can see, here is a string. So, what's the problem of this?
It expects a list of number
Yeah. Maybe we should do something like this. String representation, like A, B, D, E, C, F, G. So, any suggestions how it should look?
So yeah, I think so. You need to provide an actual binary. So if I understood correctly, it converts an actual binary tree represented as a list into a string. You are not providing a correctly formed binary tree because your root has more than two nodes. Has more than two children, so that's why it doesn't work. If I understood correctly.
Yes, and how can we fix this? So what's the input of this function?
You need to structure your input list into actual. So you need to put more parentheses in your input value.
Okay.
So like it would be only two children per node.
Example A, B.
So that's like, yeah, for example, like we can start it like this. Oh, no.
It doesn't work. So, first tree, second tree. So what's the type of this?
Yeah, this is a list.
Yeah, this is a list. So we have now.
It's empty because it's an empty string.
Yeah.
And then if it's not empty, then it checks if.
So maybe we should do something like this. Like this one. Yep.
Actually, I don't think you need subcodes in this case because if you have an outer code, it will be quoted either way.
String representation. C, B, quite, code.
We don't need any code inside this on the side.
Yes, that's true. Okay, so let's check how can we implement the binary tree. For example, check given expression represents a binary tree. For here we'll put this expression, compile. Then, for example, this tree, as you can see, we have to put into leaves a nil. Okay, so yeah, that's true. Now we can implement the null one.
We don't need it. We don't have trees.
Yes, string. Yep.
Yeah,
Now it works.
yeah.
So another problem which I want to describe with you, it's the path from one node to another node, which is graph problem, which is very useful for many different applications. graph problems in Lisp should do the following. Path from one node to another. So we will do the following: compilation, compile file. Yep. Yes. Now have to test this. Function path. Return the acyclic path from one node A to node B in the graph G. The function should return all paths. So it's not working. Why? Because we didn't define the graph. So how can we do this? There are different types of graphs here. So we can create some graph expression form as our default representation. In common Lisp, there are predefined function to work with sets. So the graph is like a set. So which is quite useful expression. So we can implement some directed graphs, some labeled graphs, and just represent an example graph, for example this one here. Put this into the comments. Yeah. And for do the following. Can we do this like def var for graph? Am I right? G. It's not working. What's the matter? Aborted on both variable G. So as you can see, there are some different issues from one case to another, and it is useful to check the solutions and try to put into the read evaluation loop. So in our example, we have this graph expression form, which represents the following. So B, C, D, F, G, H, K is connected with each other. Then other things BC, like BC, BF, CF is connected, and KF is also connected, and GH is connected. Yep. Okay, so we name the nodes, and here we name edges, yes. So the logic is the following. So if you want to put some global variable, you have to define this using def var, and in the variable graph G we will put this one. So what's wrong with this? Okay. So the parenthesis goes to the whole list. This one goes here. So what's wrong with this?
Can you replace default with list in the beginning of the first one?
Okay.
Actually, no, it will try to evaluate. No, that will work.
Okay, illegal function call.
I mean, yeah, actually, I think.
So the only way to express this is just find type the following. Yes. So, but it's unbound because it's a free variable and it doesn't know what's inside this.
It should call the whole list if it's if there's a quote outside. So can you show the graph again?
Yeah, this one.
I think there is a parenthesis missing there. So what is missing here?
Yeah.
I replaced the name, but it should be the same. So count the parentheses at the end. It's wait, no,
It equals to 3. Var maybe the name of this one. It's not correct. Maybe signature page. So let's just try this one. So, okay, due to the shortage of time, we'll express this in the chat later. Okay. So the last thing which we want to explore is the book, which is called Okazaki Purely Functional Data Structures. I would recommend you to implement those data structures in Lisp, but this book is written mainly for standard meta language, which is also a functional programming language, so it can help to understand what's the lazy evaluation, what's the strong evaluation, etc. So the program is just the data structure and algorithms. So if we know the data structures, we can handle the algorithms, just learn how it works, and then we can start programming in Lisp. Then the another part of this talk is the running ACL2. ACL2 stands for Computation Logic for Applicative Common Lisp. It's both a programming language and an automated reasoning system based on first-order logic. So it's useful for verification of algorithms, such as like software verification, hardware verification. It is useful for design validation and do safety critical systems. So how can we install the ACL2? At first we can just write the, if you're on Ubuntu or Debian, just write a sudo apt apt install ACL2. So that's it. I recommend you to install the common Lisp distribution and find the source code of the ACL2 and compile the last version for this. But for this type, for this talk, we are going to use the standard Debian 3.4 ACL version rather than the latest version is 3.5. So, what's the verification problem? As you can see, this is a block diagram of a simple algorithm that calculates the sum from the 1 to n. It returns the value of the sum from 1, 2, 3, etc. until the n, which the n is the input of this algorithm. So as you can see, at the beginning we have to assign the first value as s to 0 and the index as 1, and we have states which is called A, B, S and C of the programs. So at the beginning of the program we have the precondition n above or equal 1 because of the input of this function should be above 1, and in the output of this function we have to put a precondition like just standard arithmetic progression formula for this type of problems. So it equals n plus 1 multiplied by n divided by 2. So, and in the B state we have some abstraction which is called a loop invariant, which should hold for every possible state of the program. For every I we have following formula: I minus 1 multiplied by I divided by 2, and following condition I should be less than n plus 1, just to verify that it holds forever. How can we, the problem of the software verification is how can we logically implement the proof procedure from this statement to this statement. For this task we are using this expression which is called the invariant. For example, if we have the first step I equals 1, let's check this. If we have this following condition, put here into the formula. So it's 0, 1 less than n plus 1, because n is greater than 1, then it's s equals true. On the next step we have to prove by induction for every possible n, for every possible step in our loop the invariant holds as true. For example, we prove the base of the induction, and then we have to prove the step of the induction. Imagine that this algorithm is working for I equals some I prime, and we have, if this is true, we have to substitute it into this formula. For example, I prime plus 1 for the next step, and as you can see, it will eventually holds for some n. Then, if we prove the invariant mathematical induction for this kind of logic, we have to prove that if we put here n, I equals n, it should be hold this statement. So as you can see, you can put the appropriate value for I, and we will terminate the program. So we proved the partial correctness of this program because this is true, and if we know this one, this leads to this expression. If this is true, this leads to this expression. And we prove this by mathematical induction. We do the same thing for another theorem provers, like an ACL2, which is using the first order logic. There are different types of logics in theorem provers. For example, in Isabelle we have higher order logic functions. For ACL2 this is first order logic, The difference between higher order logic and the first order logic is that for higher order logics, we have the sets of sets. We have infinitely many implementations for the sets. Rather than for first order logics, we have just the standard logical statements and the quanters for every possible value and for and this value should be existed and the existence quanter. So this is a standard tutorial for ACL2. I recommend you to start from this page. ACL tutorial. So as you can see, we have some tutorials for this. It's standalone program for graphical user interface, for how can we support Emacs, etc. On this ACL2 tutorial, we have flying tour, which is very briefly and short, which is goes through the lines and says that it's a theory improver. We can implement some theorems, axioms inside this. This is a way how can we interact. This type of programs have states of the proofs, etc. It can be algebra, geometry, and another logical reasoning. But I think the most useful thing here is the walking tour. The walking tour is just the first step for describing the ACL2 theorem prover. And another thing, we can try ACL2 using the web interface. For example, if you open the new proofpath.org website, you can start logical reasoning from your web browser without any pre-installed things. The another interesting thing about the ACL2, let's begin. Okay, open ACL2. So, how can we connect the libraries and packages, for example, for hardware verifications? In ACL2, it is called books. So, as you can see here, we can add our library or package using this directory. So it's called books, and here we can implement new one. There are two different command lines in ACL2. First, it's a programming command line and the logic command line. We can switch between them using special commands. For example, we can answer help, and if we have some issue, we can find the documentation. For example, what's the endpoint basic function, and it will show to us the implementation of the end p, which is defined as following: is the function for proposition, which is atom x. It's some kind of the formula. Then we can start some proving. From my point of view, I would like to use some gedit text editor, but you can also find some Emacs, some ACL CDAN interface, which is just an Eclipse or Emacs plugin to interact with this read evaluation loop theorem prover. So let's start from scratch. So this is just a system command line which is displayed inside the Isabelle gedit text editor. So let's go to. So I'm using some macros to copy and paste inside this command line and type the enter. So here we defined a function square inside the ACL2. As you can see, it's the common Lisp dialect. It doesn't use the whole common Lisp language. It's in ACL2 it uses only the subset of common Lisp. Then we want to find these statements. For example, the square 2, which is equals to 4, should be equal to 4. But we can't do this directly in the ACL2. We have to define a theorem. Then we move forward with the name of the theorem, which we call the square of 2 is 4. Then copy and paste, and that's it. We proved the theorem. That's our function x in the power of 2 equals 4. As you can see, this is the output of our theorem prover. Also, we can define another function which do the following. So we define another function. We can test it using the common Lisp syntaxes. So as you can see, it implements the just application to the list. We just put a list to some list. Then we do some let statement. So we do some evaluation for the lists. So A is equals to 1, 2, B equals to 3, 4, C equals to 5, 6. And then we can check this statement. For this particular evaluation, we have the true statement, which equals true. We can do the same for any arbitrary A, B, and C. But as you can see, ACL wrote that error in top level. Global variables such as A, B, C are not allowed. We can't do this. That's why we have to define a theorem. So we define this, and the prover steps counted. We have to prove in following amount of steps. Let's check all of the steps of the prover. We use the following command: set gag mode to nil. It will type everything while we do some proving. So we can apply some rules using this type of commands in common Lisp syntaxes in ACL2. This is the example how can we try proof rule to this statement. So it says that it's not following good, so we can implement try to prove another statement. So we reduce the conjecture to T by simply rewriting associativity of app and the summary, warnings, the prover steps counted. So that means we have to continue the proving. Another example, we can define the theorem stating the equivalence of multiplication and addition. For example, we can prove that x multiplied by y apply as x is equivalent to 1 plus y multiplied by x. So it's pretty obvious that it should be true. And the first thing that how can we do this? We can do it by induction by the first argument. We will check the x, for example, at the beginning or the proving x, let it be, for example, 1. We will check this statement, and that's correct for arbitrary y. Then we do this step proving using the induction step, and it goes all in all. It will split into the goals, and we will implement another rules and define another theorems to complete the statement. I'm not going to go deeper with this proof because I just want to describe the idea of this. We can describe some chip and electronics implementations inside the ACL2 using some standard frameworks, which is called books, as I mentioned before. Let's check hardware verification. Libraries for working with hardware description languages modeling circuits. As you can see, we don't need to find the solution. We can just start. I recommend you to find the most interesting things in this list is just the symbolic simulation framework, which is using the SAT solver and binary decision diagram. RTL, it's a library of register transfer logic and computer arithmetic, which is the very core of the implementing floating point for hardware designs and other stuff. And how can we implement some registers in the CPU. But for most of the time, if we want to implement some programming languages or another compiler, it is useful to implement some proofs inside the x86 ISA package, which is the ISA model, which is like the assembler model for machine codes analysis. So here we can check the introduction, which is quite useful. And another thing is the system Verilog toolkit for hardware verification. So, as you can see, the main idea of the CPU is the architecture. So we have two main types of the architecture, which is called the von Neumann architecture and Garland architecture. Von Neumann architecture of CPUs is most likely common thing for laptops, our modern PCs, etc. Harvard architecture is mostly useful for microcontrollers, system on chips in many projects. And as you can see, the idea of these architectures is pretty the same. We have, for this von Neumann architecture, we have the control unit, which is some Boolean function. Here we have some line, which define the number of bits for this CPU. And we have arithmetic logic unit to do some multiplication, subtraction, summation, and another operations. And then we have some registers. We have some memory management unit to define this with another periphery with the keyboard, mouse, display, and printers. So ideally, our computer is just the two blocks. It's the CPU and memory, which implements the logic between this line in the bus. So what is a chip? We have few different representation of the chips. So it can be a state table. We can implement like is a state, like an abstract. We can implement this idea of the chip like an abstract finite automator. And the most useful thing for manufacturing is the structural representation of our abstract automata. So it's the thing how can we implement the actual schematics for inside the silicon. So define SQ as a function of states in each particular time. T defines as time. The phi function implements the function of changing the states. In electronics, it's called the triggers logic block. And psi, this is a function for outputs. Using the inputs and the current state, we implement the logic of this scheme. For each particular time, we have each output inside the y function. And here x is an input and q is a state function. T is time, as I mentioned before. As you can see here, we have some box. This box is a lag operator, and on this picture you can see these arrows and blocks, and this is the idea of the all chips. Inside this abstraction we can implement every possible electronic designs, and it's quite useful to understand that inside this block and inside this block there is just only Boolean functions with the fixed size of bus. All of these are equivalents. For example, for a given circuit, an input action for the form is determined and provided that in the initial position of the state code of the trigger subsystem equals 1, 1. As you can see, this is a structural representation of our automata with the subset of states, with triggers, which is our inputs, and Z is our outputs. Then we can rewrite these rules in the formula. So this is the same as the following. Then we can rewrite this in a table, for example this one, and using this table of states, define the abstract finite automata which implements the logic of this chip. So this is the inputs, this is the outputs, this is our state. For example, if we put 1, the output of 0, 0, and we goes to this state 0, 0. If we put here 1, we will in this time frame we will output 0, 1 and goes to this state, etc. So as you can see, this is the logic of this scheme, and we can implement those chips using those abstractions, using the table, and using the formula, and to use in the software to create an actual chip with actual tracing like a graph. This is a real arithmetic logic unit, the combination of the integrated circuit and this early 4-bit LU. As you can see, there are a lot of semiconductor logic gates, like an OR and A, and the purpose of in some cases to increase the cost efficiency of the chip, we have to implement some minimization of number of these elements to increase our efficiency. This is the main idea of the arithmetic logic unit. A multiplexer is a switcher between those functions. This is a full adder 1 bit. We can implement for this is the idea of the addition. So then I would like to say about how can we implement the minimization procedure for this type of circuits. For example, we have a table representation of our function, Boolean function. So one of the methods is Quine method. There are several methods for minimization Boolean functions. It's like Quine-McCluskey methods. kernel maps, etc. At the beginning we have to remember those two operations, gluing operation and absorption operation. The idea is the following: if we check this term and this term inside the complete disjunction normal form, which we get from the table, the truth table, we need to substitute this formula and erase this value. And the absorption operation, we just looking for this type of terms and substitute into another term, W. So, for example, if we have this table, we can implement the complete disjunction normal function, which is the following term, which is the logic of this. Okay, we have the 0 0 1 0, it should go here. If we have 0 0 0 1 0 0, it goes here, etc. We just check the away the 1 value and put this disjunction into the formulas. The first operation, we just find those terms. For example, as you can see, we have this one, so we can minimize this. Here we also can minimize using this term. So we are using glues operation, and the result of the glues operation will be the following. Then we want to use some absorption operation. Here we can find this one goes to with this one goes to this one. So in the end of this procedure, we will get this formula. So this is a minimized formula for Boolean function. And we can start building a structural representation of this formula. So it goes here, and this is the output of this formula. So this can be implemented like using the Verilog, like in other languages VHDL, to implement on the chip or in the field programming gate array FPGAs. So there are a few programming frameworks. We mentioned before the two ACL2 hardware books. It's the VL Verilog Toolkit, x86 ICA model. I would recommend to find the System C books and toolchains. The most modern thing to do formal verification for the hardware is the Jasper tool, which is part of the Cadence frameworks. The Jasper is the model checking tool, rather than ACL2 is mostly a theory improver using the first order logics. Difference between model checking and the theory improving, and they are using different approaches. For example, if we do some model checking, we're creating some model of the circuit and try to simulate some cases using and check the condition holds for every possible state. They are generating millions of possible states, and if something goes wrong, we will trace this, and the model checker helps us to track the bug and verify it. Using theory improvers, we are doing some abstractions, and we have to implement some total function for common Lisps. We have to implement a function that should be true for every possible state. This is a much more analytical approach, and we can use mathematical induction and possibly define a logic for infinitely many states. Another interesting approach is the Vivado IDE, which is quite common for FPGA developers, for chip manufacturing, etc. If you want to explore some research background. It's SAIL framework, which is using the Koch and Isabelle frameworks to verify RISC-V systems. But it's not really compatible with x86 architectures. So the most powerful thing to do hardware verification here is the ACL2. I will also mention about the TLA+, which is also mostly significant software for verification distributed systems, but it's quite useful to do some specification of your algorithm, just to check that your logic, your implementation can be verified from the highest point of view. Another Verilog and VHDL infrastructure, there are many different toolkits, and one of the interesting example is the Digital.js framework. For example, we can implement full adder, and this is using some visualization from the system Verilog. So this is the example of the system Verilog implementation for the full adder. So it goes here, and we can put synthesize and oops, it's not working appropriately. So maybe it okay, we have to implement some input and outs later. So on the right hand side of the screen we will see the circuit of this system Verilog code. So the idea of this approach, we can write the code to implement the circuit design. So thank you for your time, and in the next steps we can just continue to research about the ACL2, do some formal software verification of the hardware, and implement some projects. So I recommend you to do the following. So for example, we can implement a quine procedure inside the common Lisp, which is quite interesting task for as a programmer, and then we should verify that our LEU design for ACL2 is correctly implemented. We can just verify that for every possible state of our full adder we have the correct answer. We can do the following. We can define the Lisp function which do that just does summation of two numbers, and we have a circuit of the which doing the same thing, and we have to prove the theorem that if we have for all possible A and B which converted inside the dword data structure, the output will be the same as the output of this analytical function which was defined in the Lisp. So that's the idea of the verification inside the ACL2 for hardware. Maybe in the future I will show you an example how can we implement this. Okay, thank you for your time.
Thank you. Awesome presentation. I wanted to see